Direction cosines and scalar components. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already covered. In our previous lessons, we focused on the mechanics of vector operations, specifically learning how to calculate the scalar product and how to find the projection of one vector onto another. Building on that foundation, we are now moving into a very important subsection. Today, we are going to explore how to precisely describe the direction of a vector in three-dimensional space. Instead of just looking at the components, we will learn how to use the specific angles that a vector makes with the coordinate axes to define its orientation. It is worth noting that this isn't just an abstract mathematical exercise. These angles, and more importantly, their cosines, are fundamental tools. You will find them essential for understanding the orientation of vectors in real-world applications, particularly in the fields of physics and engineering. So, let's get started. Understanding direction cosines. Imagine we have a vector, let's call it vector A, which is defined in our three-dimensional Cartesian system as a sub 1i, plus a sub 2j, plus a sub 3k when this vector sits in 3D space. It isn't just pointing randomly. It actually forms specific, measurable angles with the positive directions of our three coordinate axes, the x, the y, and the z axes. To keep our notation organized, we use three Greek letters to represent these specific angles. First, we use alpha to denote the angle between vector A and the x-axis. Next, we use beta for the angle between vector A and the y-axis. And finally, we use gamma for the angle between vector A and the z-axis. Now, here is the key term you need to remember for your exams. If we take the cosines of these three angles, alpha, beta, and gamma, we call these values the direction cosines of vector A, as we will see in the next slide. These cosines are the secret to breaking a vector down into its fundamental parts. Now that we've set the stage by recalling how to work with scalar products and projections, let's dive into the core of today's topic. The mathematical formulas. To find the direction cosines, we take each individual component of our vector and divide it by the total magnitude of the vector, which we denote as the magnitude of A with the absolute value bars. Specifically, the cosine of alpha is equal to the first component. A sub 1 divided by the magnitude of A similarly. The cosine of beta is equal to the second component. A sub 2 divided by the magnitude of A, and the cosine of gamma is equal to the third component, a sub 3 divided by the magnitude of A. But you might be wondering, how do we find that magnitude itself? Well, as we've seen in our previous lessons on 3D vectors, the magnitude of A is calculated by taking the square root of the sum of the squares of its components. In other words, the magnitude of A equals the square root of a sub 1 squared plus a sub 2 squared plus a sub 3 squared. Now that we have defined what those angles alpha, beta, and gamma actually represent, let's look at the mathematical formulas used to calculate them. Once you have this magnitude, finding those cosines becomes a simple matter of division. This calculation is crucial because, as we will see in the next slide, these values actually represent the projections of our vector onto the coordinate axes. Components as projections. Now that we have the formulas for the direction cosines, I want you to pause for a moment and think about what these numbers actually represent. It is important to realize that the scalar components, a sub 1, a sub 2, and a sub 3, are not just arbitrary numbers we've plucked from thin air. They are actually the projections of the vector onto the respective coordinate axes. To visualize this, think back to our previous discussion on projections. The component a sub 1 is specifically the projection of vector onto the x-axis, which we call ox. Similarly, the component a sub 2 is the projection of vector onto the y-axis, or oy, and the component a sub 3 is the projection onto the z-axis, or oz. Now let's connect this to the trigonometry we just saw in the previous slide. From the very definition of a projection, we know that the projection of vector onto the x-axis is equal to the magnitude of vector multiplied by the cosine of alpha. Because of this relationship, we can rewrite our components in a much more intuitive way. Therefore, a sub 1 equals the magnitude of vector a times cosine alpha. Following that same logic, a sub 2 equals the magnitude of vector a times cosine beta, and finally, a sub 3 equals the magnitude of vector a times cosine gamma. This bridge between the components and the angles is exactly what leads us to the beautiful unit vector representation we are about to see in the next slide. Unit vector representation. First, let's recall the concept of a unit vector. As you might remember, a unit vector is simply a vector that has a magnitude of exactly 1. If we take our original vector, let's call it vector A, and divide it by its own magnitude, we effectively scale it down so that its length becomes 1, while keeping its direction exactly the same. We denote this new unit vector as a hat. Mathematically, we represent this as a hat equals the vector A divided by the magnitude of A if we expand this using our components. It looks like a hat equals the quantity a1i hat plus a 2j hat plus a 3k hat, all divided by the magnitude of A. Now here is where the magic happens. Remember the formulas we just looked at on the previous slide? We saw that a 1 divided by the magnitude of A is actually equal to cosine alpha, and the same applies to the other components. So, if we substitute those direction cosines back into our equation for the unit vector, the expression simplifies beautifully. We are left with a hat equals cosine alpha I hat plus cosine beta j hat plus cosine gamma k hat. What does this tell us? It shows us that the components of a unit vector are not just random numbers. They are exactly the direction cosines of the vector itself. This connection is incredibly powerful because it means that if you know the direction cosines, you already know everything you need to construct the unit vector for that direction. This will be very useful when we move into our practical example in the next slide. Now that we have established how to calculate the individual direction cosines, let's bring everything together to see a very elegant property of vectors. Real-world example, a laser beam in a room. Imagine you are standing in the corner of a room. We'll place a laser pointer exactly at the origin, which is the point 0, 0, 0. In this setup, the floor represents our xy plane, and the vertical corner where the walls meet is our z-axis. Suppose the laser beam is pointing out into the room, and we can represent its path with a vector, which is 3i plus 4j plus 12k. Our goal here is to determine the specific angles that this laser beam makes with the floor and the two walls. To solve this, we'll follow a 4-step process. Step 1, we need to find the magnitude of our vector, To do this, we take the square root of the sum of the squares of its components. So we calculate the square root of 3 squared plus 4 squared plus 12 squared. This simplifies to the square root of 9 plus 16 plus 144. When we add those up, we get the square root of 169, which simplifies beautifully to 13. Step 2, now we apply the formulas we saw in the previous slides to find the direction cosines. We divide each component by our magnitude, which we just found is 13. For the x-axis, cosine alpha equals 3/13. For the y-axis, cosine beta equals 4/13. And for the z-axis, cosine gamma equals 12/13. Step 3, if the problem specifically asks for the actual angles rather than just the cosines, we simply take the inverse cosine of those values. So, alpha equals the inverse cosine of 3/13, beta equals the inverse cosine of 4/13, and gamma equals the inverse cosine of 12/13. Finally, step 4, we can express the direction of this laser beam as a unit vector, a hat. By using the direction cosines we just calculated, we can write the unit vector as 3/13i plus 4/13j plus 12/13k. Notice how this unit vector is composed entirely of the direction cosines we found in step 2. This perfectly illustrates the concept we'll summarize in our final takeaway slide. Now that we have understood the theory and the formulas behind direction cosines, let's put everything we've learned into practice with a real-world scenario. Key takeaways. First, let's solidify our definition of direction cosines. As we saw in the earlier slides, these are simply the cosines of the specific angles that a vector forms with the positive x, y, and z axes. To make things a bit more concise in mathematical notation, you will often see these direction cosines denoted by the lowercase letters L, M, and N specifically. L equals cosine alpha, M equals cosine beta, and N equals cosine gamma. Next, let's revisit the concept of scalar components. It is crucial to remember that the components we've been working with, the 1, a 2, and a 3, are not just random numbers. They are actually the projections of the vector onto each of the coordinate axes. This leads us to a very powerful way to represent a unit vector. As we demonstrated in the unit vector representation slide, we don't need the original components if we have the direction cosines. We can write the unit vector, denoted as a hat, directly as cosine alpha I hat plus cosine beta j hat plus cosine gamma k hat. This shows that the components of a unit vector are, in fact, the direction cosines themselves. Finally, I want to leave you with a very important mathematical identity. Based on the fundamental trigonometric identity, where sine squared theta plus cosine squared theta equals 1, we can derive that the sum of the squares of the direction cosines is always equal to 1. In other words, cosine squared alpha plus cosine squared beta plus cosine squared gamma equals 1. All right, let's take a moment to wrap up everything we've covered in this lesson by reviewing our key takeaways. Now, before we finish, let's look at some common pitfalls to avoid so you can ensure your calculations are always accurate. Common mistakes. Now, before we wrap up today's lesson, I want to pause and highlight some common pitfalls. As we've seen throughout this session, from calculating the magnitude to finding those final angles, it is very easy to make small errors that can lead to incorrect results. Let's look at 3 specific mistakes to watch out for. First, be careful not to confuse the angle itself with the direction cosine. It is a very common mistake to say that the angle alpha is the direction cosine. Remember, the direction cosine is the cosine of alpha, not alpha itself. When you are working through your calculations, always keep that distinction clear in your mind. Second, don't forget to include the magnitude. When we were calculating the direction cosines in our laser beam example, we had to divide each component by the total magnitude of the vector. A frequent error for beginners is to simply state that cosine alpha equals a 1, forgetting to divide by the magnitude of a vector. Always ensure that you are dividing the component by the total length of the vector to get the correct ratio. Finally, keep a close eye on your signs. Direction cosines can indeed be negative. This happens if the angle between the vector and the axis is an obtuse angle, meaning the angle is between pi divided by 2 and pi. When you are calculating your cosines, always carry over the positive or negative sign of the original components, a 1, a 2, or a 3. If the component is negative, your cosine will be negative too. If you can avoid these 3 traps, you'll be well on your way to mastering vector orientations.